Okay, folks, let's pick up where we left off with on Friday, and we were talking about molecular orbitals. And so, what you need to make sure you remember then is molecular orbitals is just another way that we go about trying to explain then how two atoms are able to combine together and form a bond that forms these molecules that we've talked about. And so, the localized electron model with its presentation of hybridization and these hybrid orbitals is one way that we can explain how two atoms can form a covalent bond. Molecular orbitals is another way that we can go about explaining how two atoms can come together and form a covalent bond, which is the sharing of electrons. Okay? And so the fundamental difference between the two ideas, the fundamental difference between the localized electron model and the molecular orbital model here is that with the localized electron model, it proposes then that the electrons stay localized. It stays between the two atoms that share that particular bond. The molecular orbital theory then proposes then that these electrons then are delocalized and they move throughout the molecule itself, and that's what holds the molecule together. Okay, and so the molecular orbital theory then, the molecular orbital model is a little bit closer to the concept of the metallic bond that we talked about earlier, and that is the electrons are free to flow throughout the new molecule itself. Okay, so with that said, then let's make sure you understand then that the localized electron model, what we're looking at here then is that these covalent bonds, the sharing of electrons is shared within a single space. It's going to be localized. Therefore, then these two electrons here do not move out throughout the molecule. They stay between the carbon and the hydrogen here. These four electrons here, they are also localized. And they stay between the two carbons here. And so therefore, we refer to this model then as the localized electron model. And like I suggested to you on Friday, the reason why what's good about the localized electron model is it allows us to predict geometry. The problem with the localized electron model is it doesn't take into account the quantum mechanical proposal, the quantum mechanical idea of the delocalization of electrons. Electrons, like we learned back in chapter in the quantum mechanical chapter, is that we learned that the electrons we cannot predict the location and the momentum of an electron within an atom. Same thing holds true then for a molecule. We cannot be certain about where those electrons are be. We can only talk about probabilities. We can talk about how there's a higher likelihood that electrons can be located oh, excuse me, in certain areas of the atom. So we can say the same thing about the molecule, that the electrons are located in certain areas of the molecule. And so we go back to this discussion then of electron probability, electron density and probabilities. Okay? And so we will be talking about wave functions again. And so what I want to do point out, I do want to point out to you then, and when we talk about wave functions, we're considering electrons behaving as these standing waves. And so with that said then, we will be able to describe then the types of molecular orbitals that does form. Okay, and so here then, like I pointed out to you, what happens is that the two atoms they get together and they take their atomic orbitals and blend them together to form these molecular orbitals. This is unlike the localized electron model, where a single atom takes its atomic orbitals and blend them together to form these new hybrid orbitals. Okay, so localized electron model, one single atom taking its atomic orbitals, blending them together to form hybrid orbitals. Molecular orbital theory, two or more atoms get together. Two atoms, for our purposes now, two atoms get together, blend together their atomic orbitals to form molecular orbitals. Okay, so you got to make sure you keep in mind the difference between those two theories and how they are different. Okay, now there will be similarities that we'll talk about in just a moment as well, but that's our starting point here, and that's where you got to make sure you keep in mind. And so this whole idea of delocalization of electrons within a molecule is very similar to the concept of delocalization, or what we call the sea of electrons that we learned about with metallic bonding itself. Okay? So that's our starting point, and that's what you need to make sure you keep in mind. That when we talk about molecular orbitals, essentially what we're doing is we're taking this idea that we learned about atomic orbitals way back in the quantum mechanical chapter, and we're applying it now to the molecule. Okay? So if atomic orbitals represents then the probability of finding electrons at certain energy levels within an atom, Molecular orbitals represents the probability of finding certain electrons around the molecule at certain energy levels. And so what the molecular orbital theory allows us to do, it allows us, and it coincides with the data that we collect about the energetics of molecules themselves. The localized electron model does not deal with the energetics of molecules. Okay, and so that's where the molecular orbital theory it benefits us to understand it and to know it. So the molecular orbital, the localized electron model does a very good job of explaining structure and geometry. The molecular, but it leaves out the discussion of energy. Molecular orbital theory allows us to discuss energies, but it really doesn't do a very good job of explaining the geometry of a molecule. Okay, and so you got to make sure you keep those in mind. Okay, so as we go about studying this, make sure you keep in mind then that the molecular orbital model, the molecular orbital theory here has its has the data that support it, and that data comes from energetic studies of molecules. And the localized electron model has experimental data that support it based upon geometries as well. Okay, so both theories, the localized electron model and the molecular orbital theory, both theories have their experimental data that support it. Okay, and so you'll see then towards the end of this chapter that we actually end up using both, and that what we use now is a combination of both theories in order to understand the behavior and the of a molecule. Okay, all right. With that said, then we're going to treat a molecule as a single entity. And the molecular orbitals that we will discuss here are basically, remember the Schrodinger equation, and that the atomic orbitals were solutions to the Schrodinger equation applied to the atom. The molecular orbitals then essentially will be the solution of the Schrodinger equation to molecules. And so we get then wave functions. And we get wave functions, and we can treat those wave functions. We can treat them in exactly the same way we treated atomic orbitals. And that is, for example, we can say then that if there's only 2 electrons, a maximum of 2 electrons can fill a single atomic orbital. Okay? Same thing holds true for molecular orbitals. Okay? There's only 2 electrons that will occupy a single molecular orbital, and they must also have their opposite spins. So make sure you keep in mind then that we can treat these molecular orbitals in much the same way that we can treat the atomic orbitals. And so because of that, I think it'll make it easier for you to recognize how we will deal with it. I think the issue now then will be you recognizing that they are molecular orbitals, and it'll be fairly easy to recognize that they are not atomic orbitals anymore. They are a new entity, just like hybrid orbitals are new entities formed from the blending together of atomic orbitals from a single atom. These molecular orbitals here, these molecular orbitals will represent single entities that are formed, or unique entities that are formed from the formation of atomic orbitals from 2 separate atoms. Okay, all right. And so, like I said, then the way we're going to treat these as wave functions, and so therefore then the shape that we get would be basically the square of the molecular orbital wave function, okay? And it represents the electron probability, the likelihood of finding the electrons around a molecule. Okay. Let's continue on then. Let's go ahead then, and let's so again, what we're going to do is we're going to examine the electron probability of finding electrons, electron probability of finding electrons within a molecule. Okay, and what you're going to see then is we're going to form what are called these sigma molecular orbitals. Okay, these sigma molecular orbitals will be essentially the new orbitals that we find that are formed when the 2 atomic orbitals get together. Okay, and that the molecules the molecular orbitals then are used to explain where the electrons are. Okay, so in a molecule, the molecular orbitals are now available for the electrons to move through. Once they form, the electrons move these through these molecular orbitals. Okay, all right. So let's go ahead then, and let's take a look at an example here of how a particular molecule forms. So let's look at the simplest molecule that will form. Okay, the simplest molecule that will form could be then the formation of hydrogen molecule. Okay, oops, sorry, the hydrogen molecule. Okay, so let's go ahead and let's take a look at how the hydrogen molecule is here. So this is a computer-generated electron probability map for hydrogen molecules. So we're looking at the H2 molecule here, and this is the nuclei of one hydrogen, this is the nuclei of another, and you can see the electron probability cloud given us to us here. Okay, and so let's go ahead then. Let's examine then how what we're going to be looking at here. Okay, so we will be looking at and we'll be using this molecule here in order to understand molecular orbitals. We're going to look at what happens when one hydrogen. So remember, one hydrogen has an electron in its 1s orbital. Okay, and we'll call this hydrogen A to distinguish it. Okay, so this is hydrogen A, and we're going to see what happens when this hydrogen comes together with this hydrogen with its 1 electron and the 1s orbital. We'll call this hydrogen B. Okay. And so remember, we saw these hydrogens are going to start coming closer together initially. And remember the energy diagram here, and I would suggest that you go back and review that in chapter 8. Remember that we saw them with the energy diagram here versus internuclear distance. Okay. And I'll call this distance here. As the two atoms start out, they move at a certain energy level. We saw that. And then so this is the distance between them. Okay, so this is the distance between them. This is the internuclear distance. Okay, as they start out separate here, so they're separate. And as they get closer and closer together, we saw then that there's an energy dip that occurs. Okay, and then it moves up further and further. So as these two atoms get together, we see then that there's this energy minimum right here. So there's an energy minimum that exists right there. And the question is, how do the two atoms then how do those two atoms achieve the energy minimum? As they get closer and closer together, what will happen is then we'll notice then that the bond has to form. We're going to talk about that. So the bond has to form. Okay, electrons. Okay, so I'm going to draw it like this. Whoops, sorry. And like this. Whoops. Let me go ahead and redo this really quickly, folks, because I want to show you that there's a union of these atoms here. Okay, oops, sorry. Okay, so this hydrogen atom here, okay, gets together with this hydrogen here. Okay. This interaction, this is the interaction that forms the hydrogen bond. So this now is our hydrogen molecule. Okay, this is our hydrogen molecule, and it's at this position here. It's right there that the hydrogen molecule exists. The hydrogen atoms, the separate hydrogen atoms, exist here. Okay, they exist here. So make sure you remember this diagram. And the hydrogen molecule exists right here. That's where we find the hydrogen molecule. At this energy minimum, that's where we find the hydrogen molecule. Okay. So what we're going to do is we're going to use the molecular orbital theory to explain how this happens right here. Okay, how that happens right there. So make sure and keep that in mind. Okay, so as we move forward, okay, let me go ahead and erase this. Okay, let's go ahead and take a look at what happens here. Okay. Okay. So what we have here then, and I've drawn the diagram for you here, is that each hydrogen molecule, okay, and we have each hydrogen atom, sorry, has its 1s or 1s electron, okay, and it gets together, okay, and it will get closer and closer together. And as it does so, the two s orbitals, they will get together, and they will either add together or they will be subtractive. So you will either have an additive effect or a subtractive effect here. Now make sure you keep in mind that these represents the wave functions, and it's going to be the square of the wave functions that we talked about for the 1s orbital. Okay, so these are the square of the wave functions. Okay? And so what happens then is, if you treat these two quantum mechanically, we're treating these atoms then, we're treating these orbitals then as electron probabilities. These are standing waves now. I'm sorry, these are standing waves now that we were combining together. And so when you combine waves together, remember, when you combine waves together, they will either combine constructively. So this is your constructive. If you add together, this will be constructive, and this will be destructive. And that's how you can think about this destructive. Okay, and this is how you can go about thinking about how this positive and negative sign will come into play. So these two, again, these atoms, these orbitals that are treated as waves, okay, destructive. And so if they are waves, they can interact and they can interfere with each other. They can interact either in a constructive manner or in a destructive manner. And that's what this means here. So that's destructive versus constructive here. So again, the way you want to think about this is if you can want to think about how these molecular orbitals form, they form from two standing waves, two 1s orbitals coming together, and they will interact either in a constructive manner or a destructive manner. Okay, so that's how these molecular orbitals form. They form as a result. So what we have on the right-hand side here is the formation of the new orbitals. When these two atomic orbitals, and so make sure you keep this in mind, what we have on the left-hand side here are atomic orbitals. So these are atomic orbitals on both sides. On the right-hand side here, these are the molecular orbitals. Okay. And there are two molecular orbitals that form. You have a molecular orbital that forms as a result of constructive interference between these two waves here, and we have a molecular orbital that forms as a result of destructive interference between the same two atomic orbitals. So these two atomic orbitals will get together. So again, we're not talking about four different atomic orbitals here. We're talking about the same two atomic orbitals, one from the 1s orbital from hydrogen 1, hydrogen A, the 1s orbital from hydrogen B, the two different hydrogens. They will get together in the first instance here. They will get together in the first instance here, and this is instance number 1, and they will interact constructively to form what we call then the bonding molecular orbital. Okay, so what happens? This is one thing. This is one thing that'll happen when these two orbitals get together. What can also happen when the two same orbitals get together? And if you can remember, this is the hydrogen nucleus here with its 1 proton. This is the hydrogen 1s. Okay. And the second thing that can happen then when these two atomic orbitals get together is that they will interfere with each other destructively to form what's called the anti-bonding molecular orbital. Okay, and so from two atomic orbitals, we will form two molecular orbitals, and there are the two: a bonding molecular orbital and an anti-bonding molecular orbital, which is a situation that is akin, that is very similar to what we saw with hybridization. With hybridization, remember, we saw then that when you take an s orbital and you combine it together with all three of the different p orbitals, you get 4 sp3 hybrid orbitals. If you start out with 4 orbitals, you end up with 4 orbitals. Same thing holds true here. If you start out with 2 atomic orbitals, here, atomic orbital 1 and 2, you end up with 2 molecular orbitals. Okay? And so that's how you want to make sure you keep this in mind as we go through this. Okay? And so with that said then, what you're going to see then is that with the bottom case, okay, there is your constructive interference. Okay? So you can imagine then that what we have here, and folks, make sure you keep in mind, this represents then hydrogen A, the hydrogen molecule A with its one electron. Okay, this is hydrogen molecule B with its 1 electron. The electron, this is the wave, the electron wave that we talked about. And so these waves then, when they line up, remember, in phase with one another, you get this constructive interference in which, remember, the amplitude of each one of these waves increase, and that's how we represent it. So we have an increase in electron probability. What we're saying here is that we will have an increase in electron probability between those two atoms. And so let me go back here and let me make sure you understand this. That what we're saying here then is that when with the bonding molecular orbital, you have then the nuclei here, you have an increase in probability finding electrons between the two atoms, and that's what we have when we talked about this. Okay, so that's what this amplitude means. Yeah, that's what that increase in amplitude means right here for our constructive interference. Okay. For destructive interference then, let's go ahead and take a look at this. Okay, so again, what we have here is hydrogen. Okay, so this is hydrogen A with its 1 electron. This represents the electron probability. This is the electron distribution for hydrogen A. This represents the electron distribution for hydrogen B. And when they get together and they interact with each other destructively, what you notice is that the waves, the standing waves then that represents each one of these electrons are 180 degrees out of phase here and here, and so therefore then you get no no amplitude. You get a cancellation of amplitude, and what we see then is that cancellation of amplitude. And let me go back to the initial picture there, which means then in between here, right here, in between the two atoms, you have nothing. They completely cancel out with one another, which means then we have here a node. Remember we talked about that? We have a node here, which represents then a complete cancellation. We have no electron distribution between the two atoms here, and that's what we see with, and that's what we see then, sorry, with what we have here. This represents the node that between the two atoms, and I'll repeat this for you as we go through the next slide. But that's what you want to make sure you understand, that molecular orbitals form when you have two atomic orbitals overlapping with one another, interacting with one another, either in a constructive manner or a destructive manner. And that's what you want to make sure you keep in mind, so that we have the constructive interference and destructive interference that forms either a increase in the electron distribution probability between the two atoms, or a complete cancellation, in which case then there are no electron, there is no probability of finding electrons in this given circumstance here. Okay. All right. Now, I know this is a whole lot for you folks, and make sure you take a look at this video and watch it, and review, as you watch this video, review your book, okay? And so let's go ahead then and let's take a look at what we have here, okay? So we can talk about this in terms of the energetics now, and I'm running a little low on time here, so I want to finish up here with you. Where you can talk about this in terms of energetic, okay? So here's hydrogen A, okay, and remember, the way you want to view this one, then is in terms of the energy diagram that I gave you earlier. Okay, so this is going to be energy, and this is going to be internuclear distance. Okay, and let's make sure you keep that in mind. Okay, so the two separate atoms, the two separate hydrogen atoms start out separate, and then as they get together, see that dip in energy, and then it rises in that manner there. Okay, and so what we have here on the outer edges here, and the same thing with energy, is that's what we have right here. The two hydrogen atoms start out, we'll call it hydrogen A, hydrogen B, at a certain energy level here with their electrons, okay? And as they move together, they get to this bottom portion here. This energy minimum represents this right here, the molecular orbital. As soon as they get together and they form, the energy minimum here represents the molecular orbital, the bonding, I'm sorry, the constructive interference here. This is their constructive interference, between, and this represents the destructive interference between the two atomic orbitals here. So we should keep in mind then that we have these separate atomic orbitals here. These are the 1s orbitals. This is the 1s, and this is the 1s. They get together and they form our two molecular orbitals. And in terms of their energy, then the molecular orbital that represents the constructive interference is going to be lower in energy than the molecular orbital that represents the destructive interference here. This is going to be higher in energy, and there it is. There's our node. There's our node that I talked about. Okay, and so these molecular orbitals here, these molecular orbitals that form as a result of destructive interference are going to be at a higher energy level than the ones that represents the interaction between the two orbitals in a constructive manner. And as you notice then, here are two nuclei, okay, and the probability distribution here is very high. So you have an additive effect here, so we can expect then that the electrons should be, the two electrons here would spend most of their time in this region right here, okay? Whereas with the molecular orbital formed from destructive interference, there is no electron probability here, so we don't expect the electrons to stay here at all, not between the two atoms, but they exist outside on the outer edges of the nuclei here, okay? And so we can take a look at this, okay, in terms of, let me clear this out, okay, in terms of its energy, okay? And we see then that in this case then, in the case then where the electrons occupy this lower end, this is what we refer to as a pro-bonding state. This state here is what we refer to as a pro-bonding state because it lowers the energy of the electrons. Okay, so if you have the electrons here separate, okay, they are at a higher energy state than when the electrons get together and occupy this bonding molecular orbital. And so we refer to this as a pro-bonding state. And so the molecular orbitals here formed from the constructive interference of the atomic atom are going to be referred to as bonding molecular orbitals. And here then, this is an anti-bonding molecular orbital. We refer to this as anti-bonding MO molecular orbitals, because this condition here, where the electrons occupy a higher energy state, is not conducive of bonding. Okay, so remember, when electrons get together, when atoms get together, they want to occupy a lower energy state. And so when they share the electrons in this bonding molecular orbital here, okay, they are in a pro-bonding state because they are lower in energy. They have achieved a lower energy state. They are lower in energy, and so therefore electrons favor this even over their individual separate atoms. Okay, when the atoms are separate, they are in a higher energy state, so that would not be pro-bonding. But when they do get together and they occupy this molecular orbital, the two atoms form these molecular orbitals here. So the 1s orbital here, the 1s orbital here, they interfere with each other constructively, forming this bonding molecular orbital. That represents a lower energy state. Those two electrons now will drop down here instead of rising up here, or even occupying those two separate states. Okay? And so that's what we refer to as the pro-bonding state. And this is what the molecular orbital theory allows us to do. It allows us to explain in terms of energies why a bond would form between two separate atoms. In this case, then, two separate hydrogen atoms. Okay? All right, so I've run out of time here. What I will do tomorrow with this discussion is we'll wrap up this discussion of the bonding and anti-bonding states. Okay, we'll describe those a little bit more. And then we're going to go ahead and apply what we learned here to predicting whether other types of molecules will form or not. Okay, other types of simple molecules will form or not. And we're going to keep our discussion simple for right now. But you understand this concept here that you're learning now can be applied to larger molecules as well. Okay. All right. So with that said, I look forward to seeing you guys in the next video, and then we'll continue this discussion at that point. Okay. All right, folks. I'll see you in the next video.